All right, folks, for this last video for 3.2, we're actually doing some conservation of energy problems. For this unit, you're going to assume, for this part of this unit, you want to assume that the mechanical energy is constant, and then very quickly in the final two sections, we will tear that down and start to analyze whether the mechanical energy is constant or not. So I have three problems. I am going to do a little spoiler alert. When we get to this problem, I might end up flipping my page over, which if you are using the packet of guided notes, you won't be able to do that because there's more notes on the other side. So you might want to find another piece of paper or just like know that you're going to write kind of small for that problem because I didn't leave enough space. All right, anyway, from the top. We have our most simple problem, which is actually the same as the inclined plane from the last problem, from the last video. We have a ball on a platform that's moving at a initial velocity. It then rolls down a hill, and by the time it rolls down the bottom of the hill, it has a new velocity. So I have like the initial speed of the ball and the final speed of the ball. I'm going to calculate the height of the hill. Here's how I want you to approach conservation of energy problems, or energy problems in general. Identify a good place where the gravitational potential energy equaling 0 would be convenient for you. Again, you can choose literally any spot. The lowest spot that the object makes it to is generally a good thing. Anytime the object is higher up than that, there is gravitational potential energy. And anytime the object is moving, there is kinetic energy. So this ends up being the same thing as the setup from the previous video. In this unit, you are writing your own equations almost every single time. So there's no formula that you're going to apply. It's just look at the situation, analyze it for what types of energy there are, and then write an equation for that. So my equation is going to look like this. This is my initial position. There is gravitational potential energy, and there is kinetic energy. Because I'm assuming that energy is constant, that is equal to the final situation's energy, which is only kinetic energy. So this first line, you're going to write your own equation every single time. There'll be lots of repeats, but there will also be lots of variation because we're learning in this course 4 types of energy. Okay, now we have speed, we have initial and final speed. We don't have mass. That's maybe a problem, but what we're going to do is we're going to write out our energy equation. So gravitational potential energy becomes m times g times delta y naught. I don't really need the delta here. I'm probably going to stop writing it. The initial kinetic energy is 1/2 mv naught squared. And that's equal to the final kinetic energy, which is 1/2 mv squared. Now, I didn't give you the mass in this problem because I knew it was going to cancel. There is an m in every term. Now, this has come up a lot in the forces unit. You have to make sure that there's a mass in every single term before you can divide it out. If there's not, then you end up having to have a mass in the denominator somewhere. All right, I'm going to use 10 for g just to simplify things. But now that I've canceled mass, I put in my values. So 10 times h, which is the height of the platform, plus 1/2 times 2 squared, that's the initial speed, equals 1/2 times 3.5 squared. Okay, so that's my setup, and then I solve for h. What I end up with is 10h plus 2 equals 6.125. And so if I subtract by 2 and divide by 10, I get a height of 0.41 meters. Okay. Everything that happens that is important happens basically before you write a lot down. Once you have written down this line, it's basically math. Your job is to spend all of your mental energy looking at the situation, identifying what types of energy there are, and then putting that into an equation. All right, next one. We have a spring. This object is at rest when it's here, and it is moving when it's over here. This is a flat surface. Now, whenever you have a flat surface, you are no longer considering gravitational potential energy. We know the force constant of the spring. We know the speed that the box reaches when it is at a maximum. And we know the mass of the box. So based on this, and not considering gravitational potential energy, because there's no change in height, it's pretty clear that right here there is elastic potential energy and no kinetic energy. Once the block is separated from the spring, there can be no more elastic potential energy, and so there's kinetic energy there. Now, the way that a spring works is it can only store energy when there's an object connected to it that's either pulling on it or pushing on it. And so the mass here is doing the storing with the spring. Once the object leaves the spring, there's no more elastic potential energy, even if the spring is like wobbling or something. So the equation that I write is we have an initial elastic potential energy, and that is equal to a final kinetic energy. So in this situation, there's only two types of energy, and they just exchange completely. So all of the elastic becomes only kinetic energy. I can write my equations, 1/2 kx squared for elastic potential energy, and then 1/2 mv squared for kinetic energy. You don't have to, but you will end up wanting to cancel the 1/2. So you like multiply both sides by 2, and that would give you everything you need. Then we can put in our numbers. So this is going to be 12 times x squared equals 2 times 0.40 squared. So 12 is the force constant. I'm looking for the compression of the spring. The mass was 2, and then the final speed was 0.4. And so this is 12x squared equals 0.32. The initial stretch of that spring was 0.16 meters. So divide by 12 and take the square root. And so that's the compression. Okay, so the last question is the most difficult, and we'll see how that is when we talk about kinetic energy and gravitational potential energy. So we have this ball where we know its mass. We have the spring constant of a spring. So basically the ball is dropped from rest. It falls until it hits the platform here, which is supported by the spring, and then it compresses the spring by a certain amount. So I'm going to draw one more picture here. I'm going to draw like the compressed spring there. And that's like the final position of the ball. And this distance is 0.09 meters. So the spring is compressed by that many meters below the height it was at. So we're looking for the height that it was dropped at. Now, I clearly have a situation where gravitational potential energy is involved, and what makes this problem difficult is that you have to realize that once the ball starts to compress the platform, gravitational potential energy is still being lost, and so we have to account for that. I have two good options for where to make zero potential energy. It can be where the platform is before the ball hits it, and the platform after the ball is done compressing. Basically, the ball will like put a force on the platform. It will push the platform down until the spring force is enough to push the ball back up, and at that moment it stops instantaneously. So it turns out that setting gravitational potential energy equal to 0 at the very end of the problem, when the ball is done compressing the platform, is going to make for the easiest math later. And if you wanted to try this problem again later, you could set 0 potential energy to this line and see how it happens. Okay, now I have to think about the types of energy. Obviously, gravitational potential energy is happening up at the top there. That gravitational potential energy is lost all the way down until we get to 0. As the ball falls, it gains kinetic energy, and once it hits the platform, that kinetic energy is then transferred into elastic potential energy. Now, the thing about this problem is that the mass is at rest way up here, and it's again at rest way down here. So there's no kinetic energy that I'm going to put in my equation, even though there's kinetic energy during the entire problem. it's a transfer in and then a transfer out for that. What is happening at this point in time is elastic potential energy. So with this like slightly more complex setup, there's only two types of energy. There's initial gravitational potential energy way up here, and then there's final elastic potential energy down the bottom. And so we have this very simple looking equation, mg delta y equals 1/2 kx squared. And so then the complexity comes in when you start to assign values for delta y and the stretch x. So the gravitational potential energy is the weight of the ball times the total height above that starting position. So I'm going to put this number in right away, and I'm also going to put that h in. So I'm looking for the height above the platform, but the potential energy is both of these heights combined. So h plus 0.09. And so that goes in right away. And that's equal to 1/2 k times 0.09 squared. So the thing about this problem, now that we're here, is that the stretch of the spring is also part of the height that was responsible for the gravitational potential energy. Nothing else cancels, so I can start to put in all of my numbers. So the mass of 0.1, little g is going to be 10 times h plus 0.09 equals 1/2 times 130 times 0.09 squared. All right. I'm going to do a bunch of steps all at once. I'm going to multiply everything out on the right, and then I'm going to multiply these two. 0.1 times 10 is 1, and so I don't have to divide by that. I just get that h plus 0.09 is equal to 0.5265. And if I subtract 0.09 from both sides, I get that the height is about 0.44 meters. So this problem, the lessons here are when things are vertical, you have to be careful about where you put zero gravitational potential energy. And if it's a spring that's oriented vertically, you have to account for, while that spring is getting compressed or stretched, the gravitational potential energy is also changing. Thanks.